and actually makes me annoyed because I can't kick his ass at the game anymore. One of my friends mentioned, the more I get drunk, the better I play at that game. When it comes to the base set. It actually irritated the shit out of him because my 21st, I got really, really, really fucking drunk. He's like, I still couldn't beat you. You just kept carrying me, you asshole. And the point difference went from 20 to 100 difference between the two of us. Oh, wow. Okay. I don't remember any of this, but okay. Wow.
So, you might want a blank piece of paper. Does anyone need one? Do you need one?
Not good.
Alrighty. So, and I've been thinking, if we just kind of run out of time in the semester, then we won't worry about the assignment for this section. We'll see. But the final exam has something very similar to what the assignment would have been. So I feel like you will be evaluated on it regardless. So I want to step back a little bit. We went through the luggage screening example. And do you remember which? So there's a human and two machines. Which was?
It was AUS2.
So it appeared that the second machine was the best, at least looking at hit rates and false alarm rates and all those rates. What I would like to do is practice drawing the schematic, the signal, the schematic for these examples, just to get the practice doing it. Well, let's go back to one of the schematics. We'll stop here. It needs to have the two means for each of the distributions, the Z for each side, the signal and noise. Also, the D prime, which is our sensitivity. The decision criterion. And then it will also have Y for both sides. And I don't have one that has everything. So it'll show where it intersects the two distributions, and then shade in these two portions to indicate what is false alarm, what is miss. I think that's everything that I want us to cover. Now, it's not like we're going to put a scale on the bottom. It can look pretty much like this, but we need to make sure that we have things in the correct order, because while these figures and these examples are all nice and neat, and the decision criterion passes pretty close to the intersection of the two distributions, we won't see that in real life, at least not all the time. And so we need to be ready to diagram it differently if that's the case. We had talked about the way we find where the decision criterion is, and I want to make sure I get there. So, what is that? Well, we'll just talk about it. Okay, I think it was here that we talked about it. We don't have a visual. So it is possible for the decision criterion to be less than the mean for the noise or greater than the mean for signal. It's just, like I said, all of these, wrong way. All of these figures have it nice and in the middle, but sometimes it might be over here, and sometimes it might be over here. And we'll see that with the luggage screening example. All right, so just to refresh, 100 suitcases, and they planted 20 contraband suitcases in the pile. So let's start with the human, and let's write down some of the things that we'll need to know here. So we've got our correct rejection rate, false alarm rate, the miss rate, and hit rate. Right now, I'm just going to write down some numbers so we may want to go to another slide. 0.2 and 0.8. Okay. So we used that tool, the Excel formula function, to come up with our Z score and then Y score for each. So for the signal, we get Z equals negative 0.842. And what does Z represent again? Or like whether if you're looking at the graph, where it is on the graph, or what does it represent? Either one. Yes. So it's the distance from the decision criterion to our mu for the signal, at least, for this one. Z for signal is that distance. Y for signal. Well, we'll talk about Y in just a minute. Let me get the numbers down, though. So we have negative 842. For Y, we have 0.280. For Zn, we have 1.150. And for Yn, 0.206. Gonna have to get some new markers. So when drawing this, has anyone done art? Like took an art class, or you draw in your free time, like sketching? You do any sketching? Okay. I used to as well. I don't anymore. In middle school, I got an award for like the best art or whatever. Because I actually tried, but now, it was all downhill from there. So when you're sketching, does it look like what you envision in your head right off the bat? Right. It takes yeah, never. Well, hopefully, eventually it does. But I'm gonna pretend I'm sketching, but a lot of times you're using like light lines to draw something, and you're drawing lots of light lines.
Yeah, instead of one.
And when you can see the path that you actually want, then you can kind of darken that one in. So when we draw these, it's going to be kind of the same, not a sketch, but just things aren't going to be exactly where we want them to be the first time around. So a pencil might be handy just for drawing this, because we're going to have to line some things up. And I'll just use my own. And it's not going to line up perfectly the first time, probably. So we're going to have our two distributions. I want to make sure I match colors with our examples. So blue is noise. I don't have blue, so we'll use green. Green for noise. And red for signal. So red is signal in this case. And green is noise. We know there's some overlap. And that might not be enough overlap. We'll see. Yeah, yes. So we have our mean for noise. And our mean for signal. And we don't know exactly where, if we were to draw an x-axis. It's not like we're plotting where these are on there necessarily. We're just representing them. So we have our decision criterion, and don't know how, I guess my marker has done such a good job, but it's dying now. So, well, okay, I drew that line, but I should have waited just a minute to make sure I was drawing it in the correct location. So, how can we tell where we need to draw it now? And just generally in relation to the two means, do we draw it over here, in between somewhere, or on that side?
You ideally want it in the middle, but it could be.
Well, not necessarily. Just kind of depends. But what we can look at Z and Y.
Less than Z, and so it's going to mean that it's going to be closer to the mu S.
Okay, good. And is it going to be in between the two?
No,
or on a?
Because there's like a huge difference.
Well, okay, so maybe I'm not asking right. So it is, if let's take a look at this. So if ZS is negative, then it's going to be, it falls in between the two. If ZS, if ZS is negative, sorry, if ZS is negative and ZN is positive, then it's in between. But all that basically tells us is that it's less than the mean for S, but it's more than the mean for N. When they're both negative, it means it's less than both of them. So it's going to be on the left side. And when they're both positive, then it's going to be on the right of both means. So it'd be over here. Does that make sense?
Yes.
So when it's split, then it's in between. If it's negative, it's on the left. It's closer to 0 if this was an x-axis. And if it's both positive, then it's going to be higher. It's going to be bigger than both. So we have our two Z's. ZS is negative and ZN is positive. So it would be between, but you made some good points, Amy. You said ZN is a larger number. So what were you saying that tells us about its placement? Yes. So remember, the Z represents the distance from that mean to wherever that decision criterion line is. Because this is a bigger number, that means it's farther away. Then ZN is bigger than the ZS. So we would have to move it further. So it wouldn't be right in the middle like I drew it. It would be a little bit over here. And yeah, I really need to get some new markers. We are gonna have to adjust some things, but let's go ahead and label those. So we have ZN equals 1.15 and ZS is negative 0.842. So that's the distance here to this, and this is our decision criterion. So I guess I'm going to be changing the distribution if I change anything. I don't want to have to change all that stuff. So what does Y tell us? Good. So it's the height where this XC line crosses the S distribution. Oh, sorry, S and N. Sorry about that. So it crosses the S a little bit higher up. And that kind of makes sense because it's further that way. So it should be higher, and wow, so maybe we won't have to change anything. That worked out anyway. So it crosses the N right there and the S right there. And in this case, again, we're not like trying to get everything to scale. We just need things to line up on the, is it on the correct sides. So this is our YS. Oh, well, let's just write the number to 0.280. And this is our YN, 0.2206. Can you guys see it okay? Should I turn on we don't really need the projector right now. All right, so we're almost done. Now, what I'd like to do is just label. I drew the Y's right there. Oh, well. I'd like to label each of the parts. So we're going to shade in some stuff and say, okay, this is our hit, this is our miss, this is our false alarm, this is our correct reject. Where would each of those be on this graph? We're going to label under the curve of each of the distributions. So under here, what does this represent? So it's correct reject. So that it was noise, and we said it was noise. Our response was noise, and that was right. So this is the correct reject. Now, and my black line on the bottom isn't lined up perfectly, but you could imagine there's a little line right there. There are two little areas in here. There's this part where there's overlap, and then there's this part on the other side. So let's see, let me use red. So this part, they just happen to be Christmas colors. But there's that, and then there's this. Okay. What was red?
I thought that was correct because it's on the underneath the.
So this is correct reject because it was noise, and we responded that it was noise. Here.
Look back at slide 18, a little bit clearer.
Very well. Yeah, it's it's bigger and easier to see, definitely. So here it was noise, and we said when we responded it was noise, so it's correct reject. Here it is a signal, and we respond that it's signal, and so that's a hit. So it's just these. I'll just say hit. Yeah, it's kind of small, but so it's just these two parts then where we would have to figure that out. So here, if it's a miss, what does that mean? What happens when we have a miss? This is for Brittany.
Their
So think of like the
There was an alarm.
contraband.
There was an alarm, but if there wasn't anything wrong.
So that would be a false alarm. So think of the contraband. If we missed contraband in the detector, what does that mean?
Oh, you missed it. Okay.
So there was signal,
Yeah.
but we thought it was noise. Okay. So think of it that way. So if we said, if we said there was if we gave signal and there was nothing, it was, I mean, I imagine, I don't know, but I imagine people of certain ethnicities have a lot more false alarms than others. So like the little old white, I don't want to be like racist here, but I'm guessing it's just a fact that the little white old granny probably doesn't have very many false alarms. Okay. Whereas, or little kids. But other people may have a lot of false alarms. But if there was a little kid or there was a granny who had contraband, then they probably would have a high miss rate. They would probably get through all the time. And exactly, yeah. Because you weren't expecting it.
That's how some of the bombers have six bombers. They usually pick someone that you're not expecting. But female suicide bombers are just the worst.
Mm.
You're not really expecting it.
Yeah. And sometimes the suicide bomber isn't even aware that they're, a bomber, yeah. They detonate remotely or something.
That's not much television.
Yeah, that's more TV. I'm not sure how much that happens.
I haven't seen that one yet. I've seen
Yeah.
that like in 100 different FBI shows.
Yeah.
It's not the actual bomber. They didn't do it on purpose.
Yeah. Let's see. I think it was the show I saw. One of the. I mean, I probably have seen it on 5 shows, but different shows. But I think it was Lie to Me. There's one. There's one on Lie to Me that's like that. But
When an FBI, Criminal Minds had an episode on it. Criminal Minds.
Yeah, that's what.
I'm not the actual bomber. I was bombed.
Yeah, they do a lot of people.
They're been out of. They're fucking weird.
Thank God. It needs to die.
Since 14.
Yeah.
Their last season.
one last thing, actually, that I think we're missing is our sensitivity. D prime is the distance from there to there. So again, would you want a large distance between the two or small?
You don't want it to be oversensitive. Depends on the situation.
Well, I guess it does kind of depend on the situation, but I think generally if you're wanting a super accurate test, then remember we talked about how you'd want to spread these away from each other so that it was all correct rejects and all hits. So that would spread that D prime apart. So increased sensitivity would be a good thing. So for the others, we're not going to draw them, at least not the luggage examples, but I will have you draw 1 or 2 for the other example we'll go over. All right, so that we just drew the human. Now let's actually come. So these are Dr. Fogelman's drawings, but so not bad. Oh, and I think he did beta here, which we're not going to worry about that, but let's see. Is that too close? I need the hand. Or have I had the hand? I do have the hand. I just want to, yeah, okay. All right, so similar to what we drew, right? I mean, it looks like we just didn't include the numbers. We didn't write these numbers in, but we could have. So the correct reject, we could have put that number in, put those numbers in. But it looks like we got it. So if you remember, we're going to cycle back and forth a little bit here. The first machine, the correct reject was really high. So it did a really good job of rejecting when there was actually nothing there. So 75 out of the 80, it got right. So it was good at that, but it was not very good at yes, yeah. So there was contraband 20 times and it only picked it up 8. So probably not the system you want. Yeah, for not the sort of sensitivity you want for this instance. So you can see here, this is an example where both Z's were positive, ZS and ZN were positive. So the decision criterion was to the right of even the signal distribution. And you can see just comparing the shaded area here, it's also a way to visualize its miss rate, but it's much bigger, right? So this machine had a huge miss rate. It kept, like we saw with the numbers.
Machine?
Yes.
I thought it was going to be human.
Generally, yeah, humans are, this would be a human graph, probably. So we don't want the shaded area, right? We want these to overlap as little as possible. This is just an example where our decision criteria, we would want these, the distributions to be spread out as much as possible and the decision criterion to come right down through the center of the two distributions. That would minimize our miss rate and our false alarm rate. You can see, like we said, it was really good at detecting it when there was nothing there. So very few false alarms, really tiny, but a problem with the misses. And then the last machine, which was the best, we can see here. Now the graph doesn't look that different from the human. I think just the magnitude of the numbers is greater than with the human. So we had a correct rejection rate 97% of the time and a hit rate of 90%. Both of those numbers are bigger than what the human was able to do. Okay, so one more thing. ROC, an ROC curve, or receiver operating characteristic curve, is a way of visualizing the accuracy of a test. I can't get this thing to work on my computer. I don't know if it's like a plug-in, but he says, see this example, and it won't load for me. But if you are interested in checking out some more, learning more about the ROC curve and how it's generated, then you can follow the link there. Apparently you're able to adjust the numbers and you can see the curve move and update in real time or something, which is cool, but I just can't get it to work. Which line is the best? I mean, which one performed the best according to this curve? So the machine 2 did, and what the line represents is, we were talking about the area under a curve. So the area from the line down to this middle diagonal line basically represents the accuracy. The area underneath that curve down to here is how accurate it is. So you can see red, the the first machine was actually the worst, and then the human did a little bit better than that first machine. So if it was perfect, where would the green line be? Yep, it would come all the way up to the top.
I like this chart better. Like less details, but
Yeah, it is. So you can see we're plotting the hit rate on the y-axis and the false alarm rate on the x. That's all we're doing. And where that point is on this line then dictates where that curve goes and how much area is under it. It is a nice, easy way to visualize it. Couple more things before we go through another example. And maybe I'll just have you we'll do one more drawing with the other case, and then we'll call that good. So there's something called optimality and expected value. It's kind of like cost benefit ratio. Has anyone ever done a cost benefit analysis? It's kind of like it. So what we're doing is well, at least with this beta, that's not prime. I'm not sure exactly what to call it though, but beta prime is what I'll call it. So with the beta prime, we're multiplying the probabilities by these values, the cost. So for example, the probability of noise times the value associated with the correct reject minus the cost of a false alarm. So that, what would that represent? If we're subtracting the cost of a false alarm from the value associated with a correct reject, what does that tell you? We can make up some numbers too if that helps. Or just think of it. So let's suppose that let's think of cancer. What is the value of a correct reject related to a false alarm? So which would the cost of a false alarm be more than the value of a correct reject? So think of the alternative of the alternative of a correct reject is that well, that you give a false alarm.
so would correct reject be like you definitely don't have cancer? Would you have
Correct. So let's say someone does not have cancer. They get the test, and the test says you don't have cancer, versus the other where they say, oh, you do have cancer. So these two compared to each other, there may not be as big a difference. So these two numbers might be fairly similar. It would be a small number up here with the cancer example. The cost of a false alarm is high, but it's not as high as the cost of a miss, right? That's probably the highest cost. Is if they have cancer, but you don't pick it up and you say, oh, you're good. And then in 3 months they come in and they're, yeah, yes, they miss. So, so this number may be somewhat small. The value associated with a hit be really high, right? So if someone has cancer and you're able to pick it up, that's worth a lot, right? To be able to say, yes, you have cancer. We got, we picked it up, but the cost of a miss would also be really high, right? So those are both on this bottom term here. So with cancer, I'd be curious to fill in the actual numbers, but it might turn out to be, it might not make that big a difference from beta prime to the original beta here. Let's go through an example. I think that'll help make it more sense. So this is with the luggage screening. We're going to assume that picking up a hit, I don't know what kind of contraband we're talking about, if this is drugs or like bombs or something, but the value of a hit is pretty high, but the cost of a miss is even higher. So $10 million, I'm trying to, that must be, maybe, yeah, maybe we are talking about explosives here in a plane. But they're both really high. Both of these are going to be in the same part of the fraction, though. We're going to have 1,000 minus, or 1 million minus 10 million. Whereas with on the top side, they're both relative to those relatively small. So the value in getting a correct reject isn't that high. And the cost of a false alarm is higher, but it's not, I guess you have to pull the security team away from what they would be doing, and that costs $5,000. Plus you have an angry, passenger. the granny is upset, and then, anyway. So the cost is high, but I mean, again, when we compare these two across from each other, very small compared to the cost of missing. So if we look at beta by itself with just the probability of signal versus noise, we get 4. When we include this sort of cost benefit analysis, we get 0.002. So it's much smaller. And the rule of thumb here is if you have a low beta, then it's better to have a lot of false alarms so that you can make sure you don't miss. So that's basically what it's saying. If I mean, we could have guessed that with like explosives and luggage. You'd rather have to pull several people off the line every day to wand them or pat them down or whatever. Yeah. You'd rather have more false alarms than to miss one. If you had, yeah. So that's what that means when we look at this really low beta. What that tells us is go ahead and have a bunch of false alarms just so we can make sure that we don't let anything through that we don't want. Whereas if beta is high, what that tells us is we don't want false alarms, and it's better to miss something every once in a while than to have all those false alarms. Does that make sense? So high beta means just let it through. If we really think it's something, then we'll stop. Low beta means we stop everyone that looks, sideways at us, and people get upset, but it's worth the cost. So in this case, it is a yes biased strategy. So this is the equation for expected value. We take the probability of signal and include all these terms, which we were given. So if you were to do any of this, you'd be given the value terms. You would have to come up with hit rate, miss rate, correct reject rate, false alarm rate, but everything else would be, well, you would also come up with these. Remember how we came up with those? The probability of signal and the probability of noise. Well, let's go back. Well, we could get it from right here. We have 100 suitcases. 20 of them are, planted or whatever. What is the probability that after we go through the 100 suitcases, the probability of signal, which means the contraband. So noise, so 80 of the suitcases are noise. So 80 out of 100 would be, what's the probability there? Yep. So if you want to know the probability of, I mean, I didn't really explicitly say this before, but the probability of noise, for example, would be the 80 suitcases, which is noise over the total number of suitcases. And then the probability of signal would be just the opposite. So the probability signal is the 20 contraband. So we know that there are 20 signals coming down the line out of 100. Does that make sense? So that you'd also need to come up with. All right, one more example, and then we'll be done. And maybe we won't draw because it takes a little while to do that, unless you would like to draw again. Or do you think you got it? You're comfortable with the drawing? Okay, says the non-artist. All right, so semiconductor wafer. There's actually a, can I erase this? There is a facility in Prescott that treats semiconductor wafers and gets them ready to go back to the manufacturers like Intel or ON or. Good question. I actually, you know, I have like rocks that I've collected from mines that I visit, and some of the other rocks I have are just like Adolfo gave them to me because he had them. I don't know. Anyway, so not all of them are rocks that I picked up off the ground at a mine, but I try to collect stuff from places I've been. Anyway, we went there and on a tour, Adolfo was on the tour, and he talked to like the manager or whoever, and he was like, "Hey, could we get some like wafers you don't need anymore?" So like he got him to give me 3 of their wafers, and I should have brought them. But anyway, it's like a disc, a thin disc that's it's for quality control in this like a chip manufacturing process. So have you heard of a clean room?
Yeah.
So when they manufacture, the chips that go in our computers and phones and whatever, it's the circuits are super tiny. We're talking like in nanometers, the scale of the wiring and the transistors and everything on there. I don't understand it all, but if it's that small, you can imagine what happens if a piece of dust lands on it. It ruins the whole thing. So that's what the clean room is for, is keep all dust and just like everything out.
That's the worst thing trying to get in funny suits, holy hell.
Yeah. So most of that is to protect the product, but some of it also protects the workers as well. Anyway, so what they do is they take these wafers to sort of quality check their own clean room. They put that wafer in the middle of the room. And the idea is if there is any dust in the room, it'll settle, and some of it will settle on the wafer. And so after so many days, or, I don't know how long they leave the wafer in, they'll take it and they'll measure how much dust is on it. And that'll give them an idea of, are we doing good? Or like, oh, wow, we need to clean.
It's a clean room. It's not altogether clean.
Yeah. I mean, but the level of clean that they need is, beyond anything that we could, ever, we will ever experience. We'll never experience clean like that. unless you go in one of those. But anyway,
I'm good.
okay, so these are two QC inspectors, I guess, for the semiconductor wafers. They have a training simulation. So they're trainees. They have a training simulation which presents 50% defect. So instead of 20 suitcases that are signal, we have 50 out of 100 are signal. And a defect is I think to detect a defect is a hit. So here's what we've got. We're going to be comparing the two. Let's say these are interns who are like competing for the full-time position. Anyway, instead of out of 100, we've got out of 400. So intern number 1, 200 out of the 400 were noise. There was nothing. And 18 of those times, intern number 1 said, oh, that's a defect. So their false alarm is 0.09. So about 9% of the time they gave a false alarm. Their correct reject, though, was 91% of the time. And then if we look at this, so this is a problem, probably, but they did not do so well when there was actually signal. So their miss rate was 54% of the time. So 108 out of the 200 that were defective, this intern missed. And then the hit rate was 46%. For number 2, well, actually, before we go to number 2, let's just look at Dr. Fogelman's drawing instead of making our own. They don't have a rotate counterclockwise option. Okay. So this is intern number 1. You can see really low false alarm rate, but really high miss rate, which is probably a problem. We'll see who gets the job. All right, now let's take a look at intern number 2. So what differences do you notice?
Lower miss rate.
Good. So much better at detecting the actual defects, but as sort of the downside to that, this intern, he or she, gave quite a few false alarms. So now the company has the decision was just made difficult. They didn't have, one of the interns wasn't like a rock star. They both have their strengths and weaknesses. So let's take a look at intern number 2. So you can see the small miss rate. He's a little bit wonky here, but small miss rate and a really high false alarm rate. They were sort of the inverse of each other, right? Opposite problems. Maybe if they put them both together and they both get the job. Just kidding. All right, so here we have the optimality, and we get a high beta. So the value of a hit is not that high, and the cost of a miss is fairly high, but not that big a deal. Whereas correct reject, the value of a correct reject is pretty high, and the cost of a false alarm is even higher. So I guess if there's a false alarm, maybe they have to go through like a big, huge, I don't know, what is the procedure like, Amy, when going into the clean room?
Put on the bunny suit and you gotta put it in a certain order. Like you have a tag, then you have your booties, then you have the suit, and then you got your face mask, then you got your eye covers. Yeah, I think that was about it. It was pretty horrific.
So you have to say like a wind bath or something.
Yeah, the wind back.
Oh, okay.
That was weird. That sucks when you have long hair.
So-
Yeah, like really.
And you can't like put it up or anything?
Yeah, we put it out. It
Oh my
was
God.
like my boss was like, "Your hair up? Do you have a hairband?" I'm like, no, and she hands me one. I'm like, "Hey, put it up," and it just went. And there was 2 air baths that you had to go through. It was really insane.
So I'll bet if there's a false alarm in this industry, or well, anytime, or if it's a hit, or if it's a false alarm, they probably go through some intense cleaning procedure to like reclean the clean room, and that costs a lot of money.
What happened? There was
Oh wow, yeah, wow, yeah, they use some intense chemicals. Crazy stuff. So for every false alarm, it triggers the whole protocol or whatever to clean everything again. So you can guess which intern is gonna, do better at this job, right? Let's go back. Which one has lots of false alarms, 1 or 2? This is 1,
2.
and this is 2. 2 has lots of false alarms, even though 2 is really good at detecting the defects. Trainee 1, intern 1, doesn't have quite so many false alarms, and so they're probably going to value that more based on their beta prime here, 5.6. So because it's better to allow fewer hits to prevent the false alarms in this case. So a no biased strategy is preferable. So out of luck, trainee, wait, which one? Trainee 2, sorry. This isn't the right field for you. No, I don't know. But so here's the ROC. Is that? Oh, okay. This is without including that financial information, the expected value information. So actually, trainee 2 was less accurate, but because of the costs associated with false alarms, my guess is, I mean, if it was me, I would pick trainee 2. Was it trainee 2? No, trainee 1. Trainee 2 would. I'm.
Trainee 2 was too careful.
Trainee 2, yes. Trainee 2 would be gone. Trainee 1 was more accurate, and their tendencies worked out better in terms of the money. This is a general example. We won't walk through it. It's the same idea, though. Or we could if you want. Questions? So on the exam, I mean, it's not like it's a. Should probably just. I'll bring it next time. You guys can start working on it whenever you want.
How long is it?
I think it's got more than exam 2. So so the take-home portion is a signal detection. Come on.
Oh,
So
beer and wine on Sunday again?
yeah. So you'll have to find these things. I will give you the Excel spreadsheet for calculating Z and Y. So you just plug in the numbers, it will give it to you. You'll have to calculate these. Not that they're not difficult, just making sure you line up, what is probably the hardest part. D prime or the sensitivity, do you remember how you determined that? So that's both of the Z's put together, right? The whole distance across. It's both of the Z's put together. And then beta, well, beta is, there are a couple different betas we've been talking about. Yep. So it's the ratio of the two y's. It's going to ask you to do the expected value. So you've got some costs here. If a good part is discarded, it's $20. You'll have some of that. And so you'll need to calculate the other beta or beta prime to see, should you go ahead and have lots of false alarms, or is that so? Remember, with the contraband on an airplane, you don't want it. You don't want any misses, so you don't mind having lots of false alarms. But apparently, with the semiconductors, the false alarms are really expensive, so you don't want false alarms. It's okay if you let some defects through. It's okay. Yeah, so that's a way to think about it. So that's it's all take home. Again, I don't understand exactly why he labeled these this way, but they're both take home. They will both be due on the finals day. And then for signal detection theory, there is one other problem on here related to signal detection. Well, yes, no bias. Actually, this is not. This is more. This is for information processing. So yeah, that's actually all the signal detection theory that'll be on it. It'll take a little time, but I think it should be. It's doable, straightforward. Generally. All right. Thanks, guys.
For the take home portion.